All right, we're going to talk about subspaces. Sorry for the brief pause there. I was muted, of course, because it's the Zoom semester where we all mute ourselves and forget all about how to be real people. In our class so far, we've talked about vector spaces, and let's say that V is a vector space. I'll put real in parentheses here, not as opposed to fake, but meaning that the scalars that we're using come from the set of real numbers. So we've got a vector space, the scalars are real numbers, and we've got some operations here. We're going to call them circle plus and circle dot. And that's just to remind us that these operations might be pretty weird, right? We've got a set with some operations that satisfy a bunch of properties, and they may not look like what we think of as quote unquote normal addition or normal scalar multiplication. So now let's think about what it would mean to take a vector space, take a subset of it, and know that that subset is still a vector space. So let's suppose W is a subset of V, and that's what this notation means, is a subset of. And I'll take a quick moment to say that we're not going to use is an element of to talk about subspaces, because we're really saying it's a set and all of the elements are in W are elements of V, but as a set, W is a subset of V. So what it means to be a subset, I'm sorry, I keep saying subspet because I'm about to say subspace and then I catch myself. What it means to be a subset is that for all little w in W, we also have W is an element of V. And if that's true, then we can say W is a subset of V. Okay, so our big question is, when is W a vector space with the same operations? And I just realized I forgot to write the words vector space up here. That's not very good. So W is a real vector space. So if we're looking down when I just added that, I added the words vector space right up there. Okay, so our situation is we've got a real vector space with some operations. We know it's non-empty because it has to have a zero vector in it, for instance. And we've got this subset W that belongs to V. And so, you know, if we're thinking about subsets, maybe we've got the set of real numbers with the usual operations. That's going to be a vector space. And maybe we take the subset of integers and we ask, is that thing going to be a vector space with the same operations? And we'll answer that question later on. But that's kind of what we're looking at. So let's think about what conditions we would need for W to be a vector space with the same operations from V. And if it is, we're going to call it a subspace. So let's see. It's got to be non-empty. Because we know that our vector spaces are not empty. It's going to have a zero vector, right? In our definition of a vector space, we've got something that says there exists this vector that we call zero. That's the additive identity for vector addition. The circle plus additive identity. Right, so if it's going to be a subset that is also a vector space, it's going to have the zero vector, so it has to be non-empty. Okay, it's going to need to be closed under vector addition and scalar multiplication, so it has to satisfy our closure properties. And what that means is that, you know, for all W and U in W, I need W circle plus U to be back in W, And for all W in W, and for all scalars C in the set of real numbers, we need W scaled by C to land back in W, right? And I think that the book that we're using called these properties A and B, right? One is closure under vector addition, and one is closure under scalar multiplication. All right, so let's see what else let's just sort of remind ourselves what we need for vector spaces. So for vector spaces, we need, well, we have like 4 things we need for circle plus and 4 things we need for circle dot after we know that they're closed. We need commutativity, we need associativity, we need the existence of a 0 vector, and we need additive inverses, right? So every element should have its own additive inverse. For circle dot, let's see, what did we need for circle dot? We need it to be distributive in 2 different ways, right? We need to distribute over vector addition, and we need it to be distributed over scalar addition. So we need it to be distributed over circle plus for vectors and over regular real number addition for scalars. We need it to be associative, meaning that if we scale a vector by a product of scalars, we can decide whether to take the scalar product and then scale the vector, or we can sort of scale it by one of the factors and then scale it by the other factor. And we need to know that the real number 1 is the scalar multiplicative identity. So if I do 1 circle dot W, I should get W back for all W. Let's think about which of these we're going to get for free just because we are a subset of V. So some of these we're going to get for free. Well, if W, U, and V are all elements of W, then they're also elements of V. Right, we know that they're elements of V because W is a subset of V, and so all of its elements belong to V as well. And there's a picture that I have in my mind for this, right? I've got V, some abstract set of vectors, and W is a subset. So anything that belongs to W also belongs to V. And we know that that means that W plus U is going to have to be equal to U plus W. Both of those are in W because W is closed under addition, and they've got to be the same thing because we know that if they're not the same in W, they're not the same in V, and that's bad news because they're supposed to be the same in V. So this is really because otherwise we'd contradict that V. Contradict that circle plus is commutative in our big vector space V. And same thing with associativity. So if I add 3 vectors together, this should be the same wherever I put my parentheses. Because we don't want to contradict that this operation is associative in the big vector space V. So we already got 2 of the things that we need for free, and that's pretty good. So what else can we get for free? Well, let's see. So if it's closed under scalar multiplication, so I'm going to try sneakily to get my inverses in here and then show that because I've got additive inverses in here, I should be able to add stuff together and get 0. And so 0's got to be in there too. Okay, so far, what do we have? We've got commutativity. We've got associativity. Because it's closed under scalar multiplication, I know that -1 circle dot W is in W. And one of the things that we proved, or at least talked a little bit about, is that -1 circle dot W is the additive inverse of the vector W. So this means that if I take W and I add its additive inverse to it under circle plus, whatever this thing is going to be an element of W because it's closed under circle plus. And oops, that thing is 0. Well, not oops, happily, this thing is 0. So we've got both that every element's additive inverse is in here. And once we know that, we can add them together and get 0 in here. So sweet, we've got additive inverses and then the 0 vector. And then all the other things, the scalar multiplication properties, are going to kind of come along the same way. So we get distributivity, associativity, and 1 times W is W. These all get inherited from the bigger set V, meaning that if they didn't work in W, we would contradict that they work in the larger space V. So actually, what did we just show? We showed that we get everything for free once we know that we're closed under addition and closed under scalar multiplication. And this discussion that we just had is the proof of a theorem. And I think of this as the subspace theorem. And I like this theorem because it says if you want to check that a subset of a vector space is itself a vector space, you don't have to go check 10 things. You just have to check 2, and we get all the rest for free. So here's the statement of our theorem. For all vector spaces V, if W is a non-empty subset of V and W is closed under, actually, I'm going to change this. Let's say for all vector spaces V, if W is a non-empty subset of V, then W is a vector space if and only if. So let's fix this. W is a vector space with the same operations that V had. If and only if W is closed under our vector addition and our scalar multiplication. So this is pretty great. That means essentially we've got 3 things to check. We've got to check non-empty, right? This isn't going to work for empty subsets because there's no way they could possibly have the 0 vector in there, which is something that we require for vector spaces. And we want to check that it's closed under vector addition and closed under scalar multiplication. That's pretty rad, right? That's way better to prove, to have to check 3 things than 10. And our discussion that we just had about what do we get for free, that's the proof, or the basic idea of the proof there. When this happens, we call W a subspace of V. So let V be a vector space with operations circle plus for vector addition and circle dot for scalar multiplication. If W is a empty subset of V that is a vector space with operations circle plus and circle dot, so the same operations as V, then we call W a subspace of V. All right, so there you have it. That's the definition of a subspace and the quick way to check that something is a subspace.